The name of the game is to have your team's robot solve a maze in the fastest time. Now, our group just lost by a little bit to this other group, and I'm not gonna let that happen, even though the competition is over. So I'm gonna go back to the lab and build a faster robot and explain to you how it works. Now, I'd also like to know if anybody is gonna encounter the same problem in the future, what times they've gotten. Because this is pretty fast, but it's likely not the fastest. Anyway, let's get on with it now. This is what the maze looks like. There are two versions in the same board. So there's a left-handed and right-handed version. They're symmetrical. So it's 2.4 meters from this end to that end over there. And you can use a light sensor to follow the black line here. Or you could use like a touch sensor to bump into the walls and then turn and so forth. Now, the point is, and this is the robot that I've come up with now. So, there's this narrow passage straight through. So, these walls here, they don't come far enough past the middle to block the way. So, the question now is how to build something narrow enough and fast enough to go this 2.4 meter distance in the minimum time. Okay, so this is how it works. Yeah, that's pretty cool, I guess. We have the controller unit with the battery here in the middle. It's flipped upside down to have enough ground clearance for the robot. And let's start here. So we've got all the available 3 electric motors used to have as much torque as we can. So they're connected high enough to avoid the walls. And then you have this transmission assembly here at the back, and here at the front we have the front axle. It's free to spin, just resting there, and this thing over here is meant to stop, and it actually even works. So it stops the robot. Let's imagine we're moving and this is the end wall, so we cut the power just before it's about to hit the wall, and then we've got all this momentum gather up, and these little 4 sticks here, they compress with friction. So essentially we're exchanging kinetic energy into heat. So that's what stops the robot and keeps it from breaking as well. Now, this is kind of a nice accidental design feature. This front axle here is connected with just one of these rods quite loosely here, so that if these are not enough to stop the robot, this front assembly will just pop off and the whole robot doesn't break. And also you can see the screen well. Now, here at the back, oh, this is Steve, by the way, he just keeps dropping down all the time. It's probably better to take it apart a little and then show how we get the 10:1 ratio. So we've got the 2 motors on each side driving this same axle here, and the one on the top drives this one. And it's connected with these gears, which are the same size, so we don't have to worry about having different powers on the motors. And the reason for using the same set of gears on the other side as well, and more importantly here, is to avoid the gears from jumping over each other. So we divide the load by 2. Now, this shaft here drives this bigger gear here, the gray one, which has 40 teeth in it, and it's connected to this small black one over here, which has 12 teeth in it, and it spins the same axle, which is connected to the bigger one here, which has 36 teeth, and it's connected via this assembly here to the axle of the rear side, which has the same 12 teeth again. So in total we have the gear ratio calculated as such. So you may ask, why do you need a transmission in the first place, and why does the ratio have to be 10:1? Well, the ratio itself isn't that accurate and even so important, but you do need some transmission because the end goal here is to have the driving wheel spin as fast as possible to gain maximum speed. Well, getting to maximum speed has to happen fast as well, so you need it to accelerate, and that's actually more important in short distance racing. And that means we have a small dilemma here. So do you want your wheels to be spun very fast, which means you have a maximum speed, while you would be sacrificing acceleration because you have less torque? And that's the optimization problem here. Okay, we have all the motors for maximum torque available, so we can afford to reduce the ratio to have the wheel go fast, but still accelerate to maximum speed reasonably fast. And you just kind of have to go around tweaking and trying different gears from the box available here and come up with something that has a good time. So ideally you'd like to have your robot be accelerating from the beginning of the race to the end and never actually get to its maximum speed, which would be high ideally. And here's why. So we know that distance is velocity multiplied by time, which is 2.4 meters in our case, and all these four graphs here are velocity versus time, meaning that the area under the curve here, which is shaded, is going to be the distance itself, which we want to be completed in the minimum amount of time. So let's pretend that we have no gears, no transmission. Well, it's going to mean that our acceleration is high, so speed is increasing quickly. But then again, our maximum speed won't be high at all, so we're gonna waste a lot of time at that low high speed. So you put in a transmission, a few gears here and there, so you sacrifice some of your acceleration to get a higher maximum speed, but you're not really gonna get to your maximum speed because you have the wrong ratio, but you're still gonna be a bit faster than the previous case. So ideally, you'd like to have a pretty high maximum speed without sacrificing too much of your acceleration, and just when you get to your maximum speed, assuming that acceleration would be pretty much linear, that's when you're gonna have your minimum time. But then again, if you take it too far, you're gonna win a race that would be very long because your maximum speed is gonna be way up here, but then again your acceleration is very low, so the curve is pretty much flat and the area is going to be filled until it's all too late.